All right, we are at lecture number 20. There's actually only, I think, 7 more lectures to go after today. Yeah, there's 29 classes total, 2 of which for you guys are exams. 27 lectures total, so 7 more after today. We're getting down near the end. Lecture 8 today, we're going to do just a lot of reviewing. Get you prepped for today's quiz. And then lecture B, we're going to do some new stuff. We're going to start at chapter 8. We're not going to do the last section of chapter 7. Section 7.3 is called optional topics, so we're going to skip that. We're going to go on to chapter 8. Where instead of means, we're going to be focusing on proportions. Testing and estimating population proportions and differences of population proportions. Exam 1 for you guys, that's a typo, excuse me, exam 2 for you guys. That was a typo in the last slides, wasn't it? Last class's slides. Exam 2 is in 7 days for you guys. For some future class, it might be exam 3. I'm doing 2 midterms for you guys. If you haven't started studying, start today. It's definitely a more challenging exam than exam 1 was. Like the quizzes, it's cumulative, though there's going to be a heavier emphasis on recent things, but there could be some older things. You can use a 3x5 note card, both sides, but remember that's just your security blanket. Practice problems enough that you go into the test confident that you could do it without a note card, okay? It's just there to lessen your anxiety, okay? Maybe look at it once or twice, try to keep it to once or twice or 3 times. If you spend time just searching through your note card, maybe you make your writing so small you need a magnifying glass, that's not a good idea. All right, then you're not going to do well in the test. You want to know things well enough that you could do it without a note card. You will need your calculator. Make sure your calculator batteries are fresh. And if they're not, buy some new ones before them. Okay? Like before, we'll start early. 10:50 instead of 11:10 to give you a little bit more time. But hopefully people will be able to finish within, say, an hour by 11:50. But oh no, excuse me, not an hour. An hour and 20 minutes, say, till maybe by 12:10. But you can take till 12:25. All right. So let's spend lecture A mostly doing review, although I'm going to do one new type of problem that is a little extra difficult. It is a type of problem that you should be able to do on the test, though probably you would need some help. I'd have to give you some guidance in the problem statement because it is a pretty tough problem that we're about to do here after we do some reviewing. What again is the power of a test? Okay. First of all, you need a fixed level of significance alpha. Based on that level of significance alpha, which again is typically 0.01 or 0.05 or 0.1, and remember what that does, that sets the standard of evidence. The lower alpha is, the harder it's going to be to reject the null. You reject the null when the p-value is less than alpha. You say when that happens, when the p-value is smaller than alpha, that you've got statistically significant evidence against the null at that level. The smaller alpha is, the harder it's going to be to reject the null. The stronger the evidence you're going to need, the smaller the p-value before you reject the null. You're less likely to make a type 1 error in that case. The power in that case, though, is the probability of doing something correct. Being able to do what you often want to do. You often want to reject the null. That's in the back of your mind. The alternative hypothesis is your pet theory. Right? That's not always the situation, but it commonly is that you are like the prosecuting attorney. You want to convict that person. You want to show they're guilty because you think they're guilty. You think the null's false. You hope the alternative is true. You think it's true. What are your chances of correctly rejecting the null when it is false? What are your chances of correctly convicting that person when they really are guilty, when the assumption of innocence is a false assumption? That's the power. It is a probability. Power is a probability. It's a probability, notice that word there, of doing that correct thing, rejecting the null when it's false and the alternative is true. though you have to compute it for a specific alternative value. Different alternative values give you different powers. How do you pick which one you do in real life? You pick sort of the smallest, well, if it's a right-tailed test, you pick the smallest alternative value that's still an important difference from the null that's able to be, that you're able to detect or you want to be able to detect. For example, if it's like the internet sales and you're doing the new ad campaign, you're going to spend money on the new ad campaign, you're going to hope you make not just a little bit more than the old sales per person per month, but a significant amount more, an important amount more to justify your expenses. If that's $10 more per person per month, then if that's the minimal increase you want to be able to detect with your sample survey, then that's what you should set the alternative at to calculate the power, is that minimal increase in the sales per person that you want to be able to detect. If the alternative value that you're thinking about is further away from the null, if that is true, if that's an alternative value that happens to be true, it's going to be easier to detect because it's further away from the null. So alternative values that are further from the null result in higher powers. That's why you want to pick the minimal increase in sales, for example, that you'd like to be able to detect when you want to calculate the power. To make the power in your calculation as small as possible, but if that small as possible power is still fairly big, then you're happy. That's the idea. We'll talk about this more as we do the example that we're going to do in a minute. What are type 1 and type 2 errors? I always remember it this way. I think in the courtroom, you're like the prosecuting attorney. Type 1 errors is when you mistakenly convict an innocent person. The null hypothesis is that they're innocent. The alternative is that they're guilty. If you reject the null, when you should not have, because they are innocent, that's a mistake, that's an error, and that's called a type 1 error. So rejecting the null when it's true is a type 1 error. Typically people think of that as a worse error, right? As a society, we've decided to say it's worse to convict an innocent person than to acquit a guilty person. They're both bad, but if we have to make a choice, we'd rather not convict an innocent person than acquit a guilty person. So a type 1 error is that. A type 2 error is the opposite. That's failing to convict a guilty person. Failing to reject the null when you should have. Okay? Both of those are mistakes as far as your decision goes. No math mistakes necessarily. It's a mistake as far as your decision goes. What's the truth? Alpha is the probability of a type 1 error. And in all real-life examples, you decide what alpha is, at least if you're taking that approach. Ahead of time, at least with the old school approach, you pick alpha, 10%, 5%, 1%. By picking alpha, you are deciding before the fact what the probability of a type 1 error would be. And by making alpha lower than, you're making the probability of a type 1 error lower. If people will die or go to jail when they shouldn't when you make a type 1 error, bad things are going to happen. You're going to want to make alpha really low. You're going to want strong evidence, really strong evidence against the null before you reject it. A type 2 error has a probability that's related to the power. Probability of a type 2 error is 1 minus the power. Likewise, the power is 1 minus the probability of a type 2 error. They have to add to 1 because they're complementary events. In both situations, you are rejecting the null. In the power probability calculation, the null is false, so that's good. You should have rejected it. In a type 2 error situation, the null is true. You rejected it mistakenly. So they're opposite events, they're complementary events. Their probabilities have to add to 1. But just like with the power calculation, you have to assume a particular alternative value before you can actually do this calculation. All right, we're now going to do this harder type of example. Again, this is an example that with enough help on the test, you should be able to think through. I'm going to do it from scratch. Again, I want to give you some help if I were going to put this on the test. In this problem, it's a real practical problem. Where is power used? Okay? Power is typically used in choosing a sufficiently large sample size to make sure your power is high enough. Choosing a minimal sample size to get sufficient power. Here's the situation. Suppose the population standard deviation is 10 and we choose alpha to be 0.05 for a right-tailed hypothesis test. Okay? We are doing these power calculations in chapter 6 assuming sigma is known. Again, that's not really practical. In chapter 7, they do an example of how to do a power calculation when you use S instead of sigma, when you don't know sigma. But that's sort of a little extra step of trickiness that, we want to get the basics down. This is hard enough as it is. So we're skipping the chapter 7 power calculation that's more practically what's done because sigma is not known. But we're going to assume sigma is known here. It's a population standard deviation. This is going to be our sigma. I'm picking alpha to be 0.05. I've got a right-tailed test. Mu is 30 is the null. Mu is greater than 30 is the alternative. Question, how big a sample size should we choose so that the power of the test is at least 80% for correctly rejecting the null hypothesis when we assume mu is 32? How big of a sample size n? That's the question we want to answer. We know sigma. We can write sigma sub x bar, the standard deviation of the sampling distribution of x bar, as sigma over square root of n. We can plug in the sigma and get 10 over square root of n. That's going to be a relevant quantity we're going to want to find if we're going to want to find n. Okay, that's the first thing to realize here. If we're going to be able to find n to solve this question, we might first want to find what this is. That's the first thing to realize. Secondly, I would suggest drawing a picture. Pretty much every picture we draw from now on is a normal curve. Well, there will be some scatter plots in chapter 10. Or a t-distribution. What is this supposed to be? Actually, let me label it over here. That's supposed to be, what is it typically? First two words start with S and D and they're not standard deviation. Sampling distribution. Sampling distribution. Remember I said way back when that idea is never going away. Sampling distribution of x bar. It's a normal curve by the central limit theorem when n is large enough that models how the values of x bar change from sample to sample for a fixed sample size n. When mu is 30, when the null is true. It's a right-tailed test, and we picked alpha to be 0.05. So our critical value for the critical region, that you could call x sub crit, or x sub critical, I'll abbreviate critical for crit this time, is going to be chosen in this situation in such a way that the area under this curve to the right of that is 0.05. This area is alpha 0.05. That's the same as the probability of type 1 error. For a right-tailed test, you reject if the x bar value, the sample mean value, is extreme to the right. If you pick this so that this area is 0.05, your probability of being in the critical region, rejecting the null, when the null is true, is that area, 0.05. That's why alpha is the probability of a type 1 error. You reject the null when you shouldn't have. We would like to calculate, again, the power of the test in this situation, assuming mu is 32. Maybe 32 is about here. power is the probability of correctly rejecting the null when you should because it's false. We're going to assume mu is 32. The sampling distribution of x bar when mu is 32 is going to be centered on 32. So this is the sampling distribution of x bar if mu is 32. Probably should have said if here instead of when. Which sampling distribution is right? Probably neither. These are all hypothetical calculations. You don't know what mu is, so you don't know which sampling distribution is right, and probably mu is not exactly 30, and probably mu is not exactly 32. Though you are giving the null value the benefit of the doubt. You're just trying to assess evidence against that assumption. Probably neither of these is the truth. It's all hypothetical calculations. But they're hypothetical calculations that have practical consequences. If that's the sampling distribution of x bar when mu is 32, what's the power? The power of correctly rejecting the null being in the critical region, x bar being to the right of x crit. When mu is 32, when this is the truth about the sampling distribution. What's the likelihood of that happening? It's going to be the area under that curve to the right of 32. That area like that. Now I've drawn this so that it looks like that area is 5%, the black area, and the red area is about 80%. But I still don't know what n should be to make this happen. And that's the rest of the problem. But this area is going to be the power of the test, if you assume mu is 32. What should you do now? How do you solve for n? Write these areas as probability calculation symbols. Probability notation is maybe a better way to say that. We're going to set up a couple algebra equations that we can solve ultimately for this, which will help us solve for that. We want to choose n so that the probability that the sample mean is to the right of the critical value when the null hypothesis is true. That would be an error. That's a type 1 error. We want that probability to be alpha, 0.05. And we want the probability of correctly being in the critical region when the alternative value, oops, there's a typo there, sorry, mu is 30 here. When the alternative value mu is 32 is true, this is conditional probability notation, we want that to be 0.8, at least. Choose a minimal n so that this happens. So that's at least 0.8, maybe higher. These can now be written in terms of z. So it's a little tricky here. Let's see. I'd still like to write in the light here, I think. This probability, in terms of z, can be written like this. Here you're assuming mu is 30, so for this critical value, you subtract 30 and divide by sigma sub x bar. Because there you're assuming the null is true. I'm not writing this in conditional probability notation anymore, though in my mind it is still a conditional probability, mu is still 30. That's why I subtract 30 there. This one, if I convert to z, would be the probability of z being greater than x crit minus 32 over sigma sub x bar. Subtract 32, because there I'm assuming mu is 32. If I now look in the z table, I can figure out what these numbers should be, those fractions, to make these probabilities 0.05 and 0.8. Let's go to the z table now. Open your if you want. It's kind of a mess here trying to sort out with, I don't want to erase this stuff. If you want to zoom in and try to sort out the distinction between the table and the writing. Here I want the area to the right of this to be 0.05. So since the table gives areas to the left, I want to look for a 0.95. There are two numbers in this table that are equally close to 0.95. They're right here. This one is a 0.9495 and this is a 0.9505. 0.9495 and 0.9505. They're both equally distant to 0.95. Corresponding to z is 1.64 and 1.65. Go ahead and take the average of those z's, 1.645. That's okay. So that means this is ultimately going to be 1.645 right there to make this probability 0.05. For the other one, I want that probability to be 0.8. That is also an area to the right. The table gives areas to the left. So I want to look for a 0.2, which is corresponding to a negative z, and it's, oh boy, it's in here somewhere. I can barely see it. I think this one's the closest one. That's a 0.2005. This one's a 0.1977. 0.2005 is close to 0.2. Z is negative 0.84. Go ahead and use that, negative 0.84. So what does this give us? This gives us two equations and two unknowns. This equals that, and this equals that. We can solve those equations for both x crit and for sigma sub x bar. I'll do some algebra now. I think I'll do the algebra on the board. I've got another calculator with me, so I don't have to keep going back and forth here. So the system of equations is that x crit minus 30 divided by sigma sub x bar is 1.645, and x crit minus 32 divided by sigma sub x bar is negative 0.84. This can be solved. Multiply both sides by sigma sub x bar, and then for the first one add 30, and for the second one add 32. You could write x crit is 30 plus 1.645 times sigma sub x bar. And you could also write x crit is 32 minus 0.84 times sigma sub x bar. Since these are both equal to x crit, they're equal to each other, you can set these two things equal to each other. These are equal for the values that we're trying to solve for. Now just solve this equals that for sigma sub x bar. You might want to write those on one line. I probably better do that. 30 plus 1.645 sigma sub x bar equals 32 minus 0.84 sigma sub x bar. Solve that equation for sigma sub x bar. It's a linear equation in that quantity. Isolate sigma sub x bar on the left, say, and the other numbers on the right. I need to add 0.84 sigma sub x bar to both sides so that the sigma sub x bars are on the left, and also subtract 30 from both sides. 1.645 plus 0.84, you get 2.485 sigma sub x bar equals 2. 32 minus 30 is 2. We're almost done. Hang with me here. Now divide both sides by 2.485. 2 divided by 2.485 is about 0.8048. I'll go ahead and write more decimals. That's an approximation as well. We're almost done. That equals sigma over square root of n. Now we can solve that equation for n. Square root of n, if you cross multiply, is going to be 10 divided by 0.804828978, which is approximately actually comes out to exactly, when you use more decimals, 12.425. That's the square root of n. Now square both sides. You square this thing, it becomes 154.3806. That's not a whole number. N's supposed to be a whole number, so just round up. Even though this is closer to 154, round it up to 155. That's the minimal value of n that you need. So you need a sample size of at least 155 to guarantee that in this situation you've got at least 80% power. Yeah, pretty long and tricky. Pretty long and tricky here. If I put this on the test, I think I'd have to give you a lot of help. I'm not exactly sure what steps I'd help you with. Maybe I'd say you want these things. Maybe I'd even tell you that means you want these to be equal and these to be equal, and you'd have to do the algebra perhaps to solve ultimately for n. But if I did put it on a test, there would be a lot of reading to do. It would be a long problem to describe, so part of the difficulty would come with reading it and understanding what you're supposed to do. I don't know. I'm not sure if I'm going to put this on the test or not. If I do, I'll either give you help or I'll break it into pieces. You do smaller pieces, something like that. But I think this is worth going over because it is a practical kind of thing. You're planning your sampling. You're wondering how big should n be? How big a sample size do I need to get at least 80% power of correctly rejecting the null when the alternative 32 is true? That's a very practical kind of question. So that's why I thought it was worth doing. And it reinforces some algebra skills. In high schools, they often mix statistics with algebra. I'm not quite sure why, because statistics doesn't use a ton of algebra. But here's a situation where you need to use algebra. All right, so that's our review of type 1, type 2 errors in power. Now let's also review chapter 7. This is going to be real quick, just overview of it without getting into details. It's almost quiz time. Oh, more erasing. Oh, by the way, I have one more slide where we drew a picture of the situation. All right. You should know, for this quiz and future quizzes, that the standard error of the sample mean is s over square root of n. That is it's a statistic, it's not a parameter. For fixed n, it's a statistic. It estimates sigma sub x bar. It estimates a standard deviation of a sampling distribution for a fixed n of x bar. It's called a standard error. You should know that name and you should know the symbol in the equation. You should know that when we're doing a one sample t test, you compute the one sample t statistic, and this is its formula. T equals x bar minus mu over s divided by square root of n. Mu is the assumed value of the population parameter that you're estimating here. If you're doing a test, it's the null value, typically, and I've often written mu sub 0 in that context to emphasize it's the null value. If this had been sigma instead of square root of n, instead of s, then it would have a normal distribution exactly if x bar was normal and approximately for large n, even if x, exactly if x itself is normal and approximately for large n if x is not normal by the central limit there. But when you replace the sigma with an s, it no longer is z, technically speaking. It's a t distribution if you want more accuracy. We call it a t distribution with n minus 1 degrees of freedom, and we use the t table. So you should know that formula and that idea. The t distribution looks like a normal distribution. It's still symmetric, bell-shaped. It's got a little bit more spread to it, though. And the lower the degrees of freedom, the more spread it has. Ultimately giving you more cushion for confidence intervals, bigger confidence intervals, and making your p-values higher, which makes it harder to reject a null and harder to make a type 1 error, which is actually a good thing. Here's the formula for the confidence interval for a population mean. Same kind of form as always. Estimate plus or minus margin of error. The margin of error is always a special number, t star in this case, z star in chapter 6, times the standard error, has the form that we want. You should know that the purpose here is to estimate mu. Mu is unknown, we'd like to estimate it. Sample mean, x bar is your point estimate. Do this plus or minus, you get the confidence interval. And just like before, you use n minus 1 degrees of freedom. This notation here just means the t distribution with n minus 1 degrees of freedom. That's what that means. Intervals exact for the population distribution is normal, although that really never happens in practice, that it's exactly normal. So it's always just thought of as being approximately true. For large n in other cases, and when the distribution of the population is close to normal, it certainly should be very close to accurate. Here's a summary of hypothesis testing for a single population mean. Again, just big picture overview here without getting into details. You calculate your t-statistic. Notice the mu sub 0 there. That's the null value, the assumed null value of mu. You calculate the p-values in this way. For a right-tailed test, you calculate an area to the right. For a left-tailed test, technically speaking, you calculate an area to the left of a negative t-value. However, as a practical matter, you use symmetry and calculate the corresponding area over there. And then when you're doing a two-tailed test, you double the one-tailed p-value, and for the sake of using the table, you want to put the absolute value of t there. This one, when I said you by symmetry can think of it this way, could be thought of as a probability like that as well. But it's one-tailed, it's left-tailed, so you don't double. It's with the two-tailed one that you double the p-value. Double the one-tailed p-value. Two-tailed tests make it harder to reject the null. Some people always do two-tailed tests, even if they have a theory ahead of time which way the alternative should go. Just to make it harder to reject the null. Playing it conservative. You should know the formula for calculating a confidence interval to estimate the difference of two population means. You want to estimate mu1 minus mu2. There's your point estimate. Plus or minus, here's your margin of error, m. The margin of error is once again a special number times a standard error. That's the standard error of x1 bar minus x2 bar. That's the formula for the quiz or future quizzes.